On the road. Alright, so we left off with RZ bipolar zero suppression. Any questions on why that is self-clocking? Again, it's all done with the computer and how we programmed it. And speaking of that, let me do this. Gotta find this.
It's very pretty.
Well, where is it? NSM. Okay, remember I was talking to you about the bipolar zero suppression and the rates?
I do.
Okay, you see the T1 in Charlie?
Yes, sir.
It says T1 E1 group ports must be bipolar as per, and there's the standard that it goes by. The T1 line, which is AMI is considered alternate mark inversion. We're going to go over that a little bit later too. But you can see where we have that Bravo 8 Zulu Sierra, that's bipolar 8. In other words, it's throwing the bit violation at the 8th zero. And then the E1, that's the European or Japanese one, which is AMI, alternate mark inversion, or HDB3. That one is thrown in at the 4th zero. Again, you can see that these are different as far as the way the makeup is. And it can be programmed in the NSM50 using that computer that you're using in lab. Just wanted to show you that. All right. So we got CDI, which is the next one. Self-clocking. How does it do it? Logic ones are only one transition. Wait a cotton picking minute. What do you mean one transition? Oh, we still have the 0 to +5. Now we're only talking about how it transitions and doesn't use the +5 or negative or a 0 as far as being logics of ones. So with logic 1, there's only one transition within that clock cycle. With logic zeros, it's 2 transitions. So it's kind of crazy in the way it does it. Now with logic ones, this little part right here, it can be out of phase with the clock cycle. It's unusual that it is, but it can be. With logic zeros, this is where the synchronization comes into play. It's always in phase with the clock cycle. So that's the reason why we can, that's the reason why we can always say that CDI is self-clocking. So let's take a look at these. We have a 0, which means that there are 2 self-clocking, or 2 clocks, 2 transitions that happen within that 0. You can see that halfway through the clock cycle, we got 1. The start is where we see the other transitions. So here's 1. Here's 2. So there's 2 transitions within that data of 1 within the clock cycle. So with the number 1, there's only 1 transition. halfway through the clock cycle, it doesn't matter. Normally, with ones, they always start with the leading edge. You can see that we have another one. So there's the first data. When we get to the next data, it goes down. You can see that we have 3 zeros in a row, and there's 2 transitions each time, and they're normally within the clock cycle and with the clock cycle. Again, we get a data of 1, only 1 clock or 1 transition. Again, it doesn't rely on logic 1s being +5 and zeros being 0. It relies on how many times it transitions within the clock cycle depending on the data. So that's what CDI does. Most of the multiplexers I have seen use CDI to get to the distant end unless they're on fiber, and then they use NRZ. I don't know why. I'm not an engineer, but I do my best to try to understand it. CDI, self-clocking. So what are the 3 self-clocking modes now?
It's going to be RZ polar, RZ bipolar, suppression, and CDI.
Good. So those are the 3. So let's transition over to something called analog to digital. Well, analog to digital is one of those devices where we are starting to understand, and this starts back in the late 40s, early 50s, on how we started doing digital information. And it came with this guy, Dr. Nyquist, and there's another doctor that was with him that helped him with this particular theorem. And what Dr. Nyquist said is normal voice is between the 300 to 3K hertz. So when they did their sampling, what they found out is they could go as high as 4,000 hertz. And that was to cover voices that might be, pretty deep voices or pretty high voices. And being able to take these samples from at a decent rate and be able to look at transferring that information over to the carrier where it can be transmitted out, and it's more efficient that way. So with 4,000 times a second, what he said is 2 times the highest audio frequency will give us the sample rate. In our case, since it's 4K, 2 times that gives us 8,000 samples per second. That's what we rely on. Any more than 8,000, he had problems called fold-over distortion. And if you get into, I think it's called delta modulation, you would see that, because delta modulation cannot keep up with the frequencies. It was when, and believe it or not, you guys were working with the PRIC 150, it uses something called CVSD, which is the best form of analog to digital in PCM, pulse code modulation. It can keep up with the changing of the analog signal. So you have PCM in the PRIC 150. Didn't know that, did you? Now you do.
No, sir.
All right, pulse code modulation. In order for us to get the analog over to digital using the Nyquist theorem, we're going to do it in 3 steps: sampling, quantizing, and coding. So the first one, remember this, sampling? Well, what we're going to do is we're going to take 8,000 times a second, and we're going to use something called PAM, not Peter Pan, but PAM is in the spray for your skillet. And this is pulse amplitude modulated signals. You can see each of these dots is a representative of the analog signal. And again, they're in sequence, and they are spaced equally apart in 8,000 times. So this signal now is going to be represented by these samples here. So this analog waveform is now going to be represented by the samples. So that's the first step. When we get into the second step, we're going to put it on a decimal chart. Now, it's called a quantization table, and it goes from a plus 127 down to a negative 127. Now, the easiest way to explain it, in my opinion, is taking a graph paper and applying all those numbers to it. And you can see with each one of these, it is every one of these spaces between these are equal. Every one of this height are equal. So that's the way the quantization table works. This is called uniform quantizing. You go from 0 to plus 127 and 0 to negative 127. Now, it contains 254 steps. That's basically 127 times 2. Well, how do you get 254 steps? Good question. We'll see here in just a minute. We have two different types of tables that this particular waveform fits on. One is uniform, the other is non-uniform. I showed you the uniform, so let's take a look at some of the problems we might see. Well, when we put these samples on here, you may have these samples that fit in a place where they don't quite reach the line to apply that decimal signal or the number that we need to put it at. These are called quantization errors. Hence the word on a quantization table. Quantization errors. What do? Well, you either round up or round down depending on where that signal fell in the line. Of course, obviously, it's what 5 and above rounds up, 4 and below rounds down. That's pretty much the way things work in mathematical equations. So that's what's going to happen. What does it sound like? Well, if you were to take a look at a spectrum analyzer on this, you would see distorted waveforms in that particular area. It wouldn't sound very good. But in voice, you don't really care that much about it. You just want to know, hey, did he say Bravo? Did he say Zulu? Did he say, fill in the blank there? Can you understand what the dissonant is telling you? Well, he figured out a way to eliminate most of those quantization errors by going to what's called a non-uniform quantizing. What does it mean? Well, he took the table. It's still the same space from 0 to 127 in the plus and the minus. But in his case, he started pushing the lines together. So that way, most of the voices will fit in an area where it will hit the lines. And what happens is it corrects for most of these quantization errors, so you get a clearer signal. So you don't hear garbled mess at the dissonant unless it's, a lot of the noise on it.
So would a value on a uniform be higher, so with the non-uniform, since it pushes it together, would the same value for both be a higher number on the non-uniform?
You would have more quantization errors on the uniform table than you would the non-uniform.
Right, but because the non-uniform pushes it together, are you going to reach higher numbers then?
Well, no, it's the same numbers. From 0 to 127 on the plus side and 0 to negative 127. You're not going to have more lines. You're going to have the same amount of lines. The difference is you've done, each one of them had, from horizontal and vertical, all of them are matched. But in this case, we still kept the vertical portions in sequence, but the horizontal lines we squash together where our normal voice is, because our normal voice is between 300 to 3K. Okay, so he still has the same height from 0 to 4,000. We're just going to have some issues with where it, where you got a voice that's really high or really low. Yeah, you're probably going to have some quantization errors. That's on the non-uniform. You're not going to have as many for a normal voice where most people are. Remember now, this is built for the mass. This isn't built for individuals where you get that. Now, if you wanted to sample more, let's say 16K, yeah, you're probably going to be at a better quality, but why? That means I need more processor speed, wouldn't it?
That is correct.
Yeah, the more you sample, the more processor speed that you need. So that's the reason why the uniform versus the non-uniform came into play. They figured that part out and was able to squash all those lines together to get the quantization errors. In result, clearer communication. That's what it amounted to. And I'll go over the analog to digital information here in just a minute. On a gee whiz note. That kind of cleared up?
Yes, sir.
Okay, the last one is encoding. So now we've taken the sample and we've taken it and put it on a table, given it a number. Now we got to put that number into an 8-bit word. Well, first of all, the first 7 bits equals out to 127. That's 1, 2, 4, 8, 16, 32, 64. If you add all those numbers together, you will come up with 127. Well, wait a minute. How do I get 255? The 8th bit, that's at 128. Gotta love it, eh? That 8th bit tells us whether or not we're at the plus side or negative side. So let's take a look at this. You will notice this chart right here. You can see the numbers being applied on the table. And over here, starting from the right to left, we're going to take a 2. That's this one right here. There's a 1. There's 2, 4, 8, 16, 32, 64, 128. Well, that's a number 2. That represents that. The plus says, you notice that all the pluses are zeros and all the negatives are ones. It's an engineer thing and the way they've come up with it, so that way they can differentiate between what's a plus and what's a minus. Now you would think on the common sense side, well, gee, if it's plus, it should be a logic of 1. I don't know what they came up with as to putting it as a 0. There had to be some reason. I don't know what it is. So that's how we do this. 3 steps for PCM. Step 1 is
Sample.
Step 2.
Quantize.
Step 3.
Encode.
Okay, so what corrects for the quantization errors?
What corrects for it?
Mm-hmm.
Do you mean like in what steps or what process?
What's the process?
Is this a round of the pamples?
You're getting there. Okay, what did I explain about rounding? Rounding is the quantization errors. How do I get rid of most of them?
You use the non-uniform.
There you go. You use the non-uniform table. Non-uniform quantizing table. Good. So let's take a look at these next 2 before I give you some information on analog to digital and what I just went over. But I want to go through frame period Frame period talks about the time it takes for one frame to occur. That's a definition. How do we get it? Well, just like we did the Nyquist theorem, we got 8,000 times a sample. In our case, the sampling rate is the frame period. So we have 8,000 frame periods. Now, the way we get a mathematical equation of how long it takes, we get the 8,000 sampling and take the reciprocal of it, which is the 1 over. And what we end up with is a frame period. That's how long it took. In our case, when we divide 8,000 into 1, we're going to get 0.000125 seconds, or in our case, 125 microseconds. Okay. In other words, it took me this long, 125 microseconds, to have one frame. Now, a standard multiplexer is 24 channels. It doesn't mean that you can't have some that are less. For example, the NSM, the max it can have is 12. Well, that really sucks. Yeah, it does, but that's the max that they can have. The one that I told you about, which was 16. Now, the frame period that it's going to take for the NSM versus the FCC 1000 versus the, fill in the blank, a 24 channel, is going to be all different. So everything is based off of the multiplexer channels to get what's called pulse modulated sample period. In other words, it took me 125 microseconds to get 24 channels sampled. Now I want to take and look at channel 1, how long it takes to sample it. So the definition, the time it takes to sample one channel in that frame, is all based on the number of input channels. In our case, the standard right now will be 24 channels in a multiplexer, but it can change. The way this works is I take the frame period, which I just had, and I divide it by the number of channels. So in our case, we're going to take 125 microseconds and divide it by 24 channels, and we get 0.0000528 seconds, or 5.28 microseconds to do one channel. One.
That's pretty confusing.
Okay. Frame period is all the channels. Pulse modulated sample period is select one of those channels. That's how long it took to sample that one.
Okay, and what is the channel?
Okay, channel's what you're inputting. For example, the NSM has 12 NRZ slots. Okay, so if you put all 12 of them in, then that is your channels. That's 12 NRZ channels that you've got to put in. You can put multiple users in it, but you only have one channel in that when you're dealing with users versus channels. Remember, you can have multiple users in a channel, but you can't have multiple channels with a user. You can have single users with channels, but you cannot have multiple channels per user. Channels are what you're inputting or taking out.
Okay, so it takes your input, which is made up of 8,000 frames or whatever, and then the PMSP just takes one of those selects and it calculates how long it takes.
Yep. So first of all, the frame, how long it took me to get from channel 1 all the way to channel 24. And then that was that frame period. And then I want to know how long it took me to get channel 1's sampling rate done.
So just for clarification, when we were looking at the RZs and the NRZs and stuff, that little table we saw with the zeros and ones, is that a channel?
It could be.
from one, but that would just be one person. Of
That would be one
yeah.
person, yeah. It could be multiple aggregates coming into multiple channels.
So you're getting the same frames per second as the other people in your channel usually?
Yep. So if you had, let's say, in a 24 channel, and you had, let's say, 2 users in one of those channels, you can split the 5.28. That's how much each time, let's say both of you are online at the same time, typing stuff and sending stuff at the same time. You're going to have to split that 5.28 seconds, microseconds. It can be done. Remember now, you're dealing with how many's in the dorm, and you're being able to get online and talk to me and so forth and so on. So it happens at a blink of an eye, because microseconds is pretty doggone quick. Let's look at, when we look at 125 microseconds, that's pretty quick, isn't it? In other words, if you had everybody online in a dorm in your side of the house there, 125 microseconds, that's how long it took to do everybody in the dorm. Remember, everybody's not constantly streaming. They're uploading and downloading, so to speak. You got ones and zeros going a lot faster than that. I'm sure that they've got something a lot faster in the dorms, but they just have a lot of users. That's the big thing about it. Any other questions there, Aaron Mills?
I mean, it's a tough concept to understand in the short period we've been given, but for now, I feel like I get the general concept of it.
Okay. General concept is you bowl a frame, right? How long did it take you to bowl a frame? Half an hour? How long did it take you to do one of those frames? 10 minutes? 5 minutes? You ever bowled? Let me ask you that.
I don't know what you mean by bold.
Okay, bowling, as in throw a ball right down that lane and hit the pins and all that kind of stuff. Okay?
Yes, sir.
You got one great big frame, and then you got frames within each one of them where you can either throw one ball or two balls depending on how many pins you hit. All right? So how long did it take you to do one of those versus the whole thing? That's basically, frame period is the whole game. PMSP is how long it took you to bowl one of those.
Right, it's one little snapshot.
Yeah. So
okay, so why is frame period even a unit? Like, why don't they just use one of the units we already had to distinguish time? Do you know what I mean? Like, there's so many units we have now for a time period where a frame period is just another unit of time in a way now, right? Because it doesn't change. It's always going to be 8,000, right?
Well, it can change. How many has ever heard the program Audacity?
I have, sir, yes. Isn't it like recording software?
Well, it can be. Okay. You see that? That's an audio signal. If I was to export it as an MP3, let me see if I can blow this up somehow. It won't let me, will it? Dadgummit. All right, I'm not sure you can see down at the bottom here. Wish there was a way to... Oh well. Anyway, down here where it says quality, that is a sample rate. You can do 145 to 185 kbps. It's kilobits per second. That's a far cry from 8,000, isn't it?
Right.
My processor can handle all the way up to what's called insane at 320K. Now there's other software that can do more, but this is a free version that you can actually look at and go, holy crap, yeah, it's 8,000 versus nowadays. And I'm going to go back in history here. When CDs came out, my CD player, I bought one of the first ones, had 8 kHz sampling on it. And I thought that was freaking awesome. Well, as these players started getting more and more better at it, they got more and more expensive too. Why? Because now it went from 8K to 16K, 16K to 32, 32 to 64. The last one I saw was 128, and what I paid, I think $50 or $60 for my 8K, that 128K, I was looking at it, and I think the cost was around $300. So you're going to pay more for it. I mean, it's just like computers. When you look at a processor, how fast your processor is determines on its sample rate, how quickly it can do what it needs to do. Some of them come up with, like 3.2 gig as your processor speed. Well, it's also looking at how many lines you can put in and how much information that you can process. So the more lines you have, the more processing that you can do, but your processor has to handle it. That's a lot of ones and zeros coming in there. With, this is just a simple program, the Audacity one, where you can do recording and do clips and whatever, is also based on your processor speed and what your processor can do. So when you look at 8,000 times a second, it's a standard for getting our voice over to digital, where it's easier to modulate and send out. No, maybe. No. Yes, maybe.
Yes, no, maybe so.
I'm trying to think of another way of being able to make that statement and get you to understand it.
All right, that helps. We just got a lot of info today, that's all.
Oh yeah. Oh yeah. And by the way, we are completed for the information on 1 Bravo. We've gone over multiplexing terms, data relationships, types of multiplexing, modes of TDM, demultiplexing, signal formats, and analog digital conversion. That's a lot. Yeah, agreed. A lot longer than I like to do, but I normally have this done anywhere between 2 hours, 2.5 hours. This is about right. I really like this class because you guys are challenging me, and thank you. It's unusual to get one like this.
Education first.
Oh yeah. If I can get you to understand it instead of memorize it, I have done my job. Because when you get on the test, it's a lot easier to go, oh, I get that. I understand that question, and I know what the answer is. Any questions?
No, sir.
All right, so here's what we're going to be doing Monday, 10 to 11, SIA. 12:30 is when class will start. Have homework for 1 Alpha and 1 Bravo completed. We'll go over it first thing. And then we'll have it as far as going through 1 Charlie, delta into alpha. Make sure that you have, like I showed you today, my NSM 50 tech manual. Make sure that you have access to it. Anybody not download all the information like your tech manuals and tech orders and that?
Haven't done it just yet, but I'm going to.
Okay, I think it's in resources that you can get it.
Yeah, it's just a shared doc, right?
Right.
It's under course materials.
Yeah. And if you can't find it, just let me know and I'll send it to you through Discord. And if there's anything over the weekend that you want to ask, I will tell you right now, normally I am online all the time. On the weekends, yeah, you're going to see me with the green dot on the right-hand side, but during the morning is the best time, or late afternoon, early night is the best time that you will see me. You will message me, and within, I would probably say 5, 10, 15 minutes, I'll message you back. Why? Because I play World of Tanks. And I'm normally on.
A gamer at heart.
Well, you know, I haven't played in probably about 2 weeks now because I've been so busy with course material and working on the house. So it has taken a back burner for a little bit.
Not for long, sir.
That's right.
And that's fine.
Any questions?
One quick question. What material should we be downloading off of the student materials?
Make sure.
Block 7.
Yeah.
I don't know if you need to download, just access it.
Oh, okay. I thought you were saying that we needed to download it.
You can download
Yeah, it's
it.
like I've got access to it, yeah.
Yeah, I would recommend that you download it. And the reason why I say download it is you can highlight it on your PDF, you know, on the PDF, so that way it's reference for you when you go over the information. Because sometimes, I mean, I go through the tech manual with it as well as the tech order, so that way you have a clear understanding of where the device or where the information is versus having to do a control F and see like 200 pop up for you to muddle through.